Question 7 from section 2 of the 2023 Higher Physics Examination from the SQA. Beta decay occurs when a neutron in an unstable nucleus decays into a proton and releases an electron and an antineutrino. The following statement represents an example of beta decay, and you can see what's happening there. For 1 mark in A part I, we have to determine the number represented by P. Quick revision then, if we've got the element Z and we've got a number up here, this is going to be the mass number. And the mass number just really tells you how many protons and neutrons there are in that particular nucleus. The bottom number is the atomic number, which really tells you how many protons are in the nucleus of that particular element. And that's the number we're going to be looking for here. So to do this little equation work here, we have to just balance the left hand side and the right hand side of the atomic numbers. So we look at the left hand side, we have got an atomic number of P. And on the right hand side, well, we've got the atomic number of 54. And we have an atomic number of -1, and we can ignore the neutrino. So from that little equation there, we can see that P must be equal to 53 in order to satisfy that particular element equation there. So the answer to that first one is going to be 53. Now the second part of this, it says identify element Z. Now to do that, we've got the atomic number, and that can identify it, but as we go to the periodic table, which will be in your relationship sheet, there it is there, and we're going to look for an element which has got an atomic number of 53, and I can see it down there, and circle it for you, and it's going to be iodine. So identify element Z has got to be iodine. So, 2 marks already. The second part of this question, part A, it says in the standard model, state the type of fermion that includes electrons. Well, to do this, we have to look at our chart. Just have got to remember it. There's a chart there. And you can see that the electron is in the family of leptons, which belongs to the family of fermions. It's just something you've got to learn all the buzzwords for that. So study the chart, and it says in the standard model, state the type of fermion that includes electrons, and that fermion which includes electrons must be the lepton family. Okay, and that's us done that question. 3 marks. Question 7, part A, B. W bosons and Z bosons are the force mediating particles associated with beta decay, and we have to name the fundamental force associated with beta decay. Well, that's the force which is, of course, responsible for nuclear disintegration. So what we've got here is what we call the weak nuclear force. So that is the force which the W and Z are responsible for, the force carriers for the weak nuclear force. And that's your answer for that one. Let's look at number 7, continued, part B. It tells us here we have got a positron emission tomography, PET, is a medical imaging technique which uses isotopes that emit positrons. Suitable isotopes are produced by bombarding a target with protons that have been accelerated in a cyclotron. And a cyclotron consists of 2 D-shaped hollow metal structures called Ds. You can see them in part of the diagram here. There's one D, there's the other D. And these are placed into a vacuum. Now the diagram shows the cyclotron viewed from above. It was a bird's eye view looking straight down on it. Now protons are released from rest at position R and accelerated through or across the gap between the Ds by a voltage of 32.0 kilovolts. So you must have a positive number here. This part of the D must be positive, and this must be negative in order to accelerate the protons across. The electric field must be going across this way. If you can draw it in, there's the electric field go across that way. So we're asked to determine the speed of the proton as it reaches S, and it's for 5 marks. Now, first of all, we have to calculate the work done on the proton by the electric field in moving it from R to S, and that work done will eventually appear as energy, as kinetic energy at S. So our first task is to work out the work done in the field moving the proton across R to S. That's easily found out. Work done is going to equal to QV. So we can put in our numbers for that one. The charge on the proton is 1.6, and it's going to be 1.60 times 10 to minus 19. And we're multiplying that by the potential difference across the Ds, which is 32 kilovolts. So it's 32 times 10 to the power 3. So we work that on a calculator, we get an answer of 5.12 times 10 to the minus 15 joules. So that's going to be the work done on the proton, and that is going to be transferred into kinetic energy. So that's going to be transferred into kinetic energy. So at position S, the proton's going to have kinetic energy exactly equal to 5.12 times 10 to the minus 15 joules. So we know the expression for kinetic energy, EK, is going to equal to 1/2 times the mass of the particle times its speed squared. And we're after the speed of that particle. So we rearrange it. And this is something you have to just keep practicing so you can do this autopilot method. So to change to get V squared, first of all, we double the kinetic energy to remove the half from the right hand side. And we're left with mv squared. Then we divide by m to give the V squared on the other side like that. Once we've done that, we can take the square root of this to get V is, I'll just over here for you, so the speed is equal to the square root of double the kinetic energy divided by the mass of the particle. Now we know the kinetic energy is actually equal to the work done on the proton, so our numerical sum will be bracket 2 times the kinetic energy, 5.12 times 10 to the minus 15, put that in a bracket and cover this with the square root sign, and divide that by the mass of the proton. And the mass of the proton from the relationship sheet, the data sheet, is 1.673 times 10 to the minus 27 kilograms. Now if we do that on our calculators, we end up with a speed of the electron to be 2.474 times 10 to the power 6 meters per second. We can actually make that a wee bit more to 3 significant figures by saying it's 2.47 times 10 to the power 6 meters per second. And that will be the speed of the proton when it reaches S in that right hand D. 7 Part B continued, Part 2. Explain why an alternating voltage is used in the cyclotron. Well, let's take a close look at the map of the cyclotron. Now the proton starting here at R, in order for it to be accelerated across that gap, the electric field, which I'm going to show in blue, has to be in this direction here. It has to be right across like that, because the arrows in the electric field show you the direction where a proton, a positive charge, will be accelerated. So in this particular case, we must have the alternating supply plus, and it must be then minus here. Okay. Now when the proton gets to S, the magnetic field, as we'll see in the next part of the question, bends the proton round to this position here. Now if you look very closely then, it's not going to accelerate across that gap because the electric field is in the opposite direction. So what has to happen is that the electric field has to change, and that's why we have to have an alternating supply. So when the proton gets to this position here, the supply must change, and it must change the field direction. So what we have is this. When the field changes, it's got to be plus here and minus here in order for the field to be in this direction here, with the arrows going across the way from S to R. Now once it's in that position, this being plus, that being minus, then the proton can move across, it's accelerated across the field. And once it gets to this position here, it's going to be bent round again to this position here, and guess what? The field has got to change again. It's got to go plus and minus here, so that the field lines will change, so that the proton in fact will be accelerated across the gap. So really you have to keep ensuring that the electric field between the two Ds is in such a position that the proton will be accelerated across the gap, and to do that we have to keep the alternating supply going, which means we've got an alternating electric field. Now part C is what we've been talking about then. It says a proton enters a region of magnetic field as shown, and we've got to determine where it's going to be bent, in what direction. It says determine the direction of the force exerted by the magnetic field on the proton immediately after entering the magnetic field. Now we've got a choice here using the right hand or the left hand. The way I remember it is, if it's a positive charge, I use the left hand because I think of Elvis Presley. You might know about him, but when Elvis was on the stage in the big hall in Las Vegas, and when he left the stage, there was always announcements saying Elvis has left the building, and there was always a cry from someone saying, are you positive? So when we are dealing with a proton, a positive charge, we use the left hand rule. And the left hand rule is very simple. If we look at the magnetic field, it's pointing out, so we point out of the screen. Very hard to show in this diagram, but our left hand first finger is pointing out, and the proton is going to be moving from right to left. So it looks like the proton, my thumb, is pointing up the way, so it's going to be deflected up the way. So just practice your left and right hand rules to determine where the proton is going to go.